So far we have looked at certain kinds of software design patterns. In this case we are going to look at something again in the domain of software, but at a slightly higher level in terms of how the overall architecture of a system itself could be designed. Now there are a few examples over here, and I'm going to jump straight into taking those examples and looking at how they define different patterns that could be used in order to design a system. And one of the most basic architecture patterns in terms of how a large software system is designed is called the layered architecture. And the idea behind the layered architecture is simple. What it says is you have hardware. Now in order to interact with that hardware, you basically define something called drivers, driver functions, right? And a related notion is something called the operating system. Now what exactly are driver functions? It could be something which basically just encapsulates the memory layout corresponding to a particular peripheral, right? It might have, typically drivers have some kind of standard functionality which says, if you want to activate a particular peripheral, do this. If you want to read from a particular peripheral, use this kind of standard, read from these memory locations. If you want to write to it, do this, and so on, right? For those of you who have used some kind of Linux based OS, or in fact, looking at it from the point of view of C programming in general, right, part of the core nature of C comes about from the fact that a lot of things can be abstracted in the form of files, right? So even something as simple as a temperature sensor, you could potentially think of it as a file that you open and you read from it. Of course, it probably doesn't make sense in that case to write into the temperature sensor file, but the fact that you can just open it like a file and read from it means that you have now abstracted the temperature sensor to look like a file system, right? And the corresponding drivers need to be written, but after that everybody else can just use them in a standardized way. So having some kind of drivers on top of the hardware means that your first level of abstraction has now been achieved. You could then build certain kinds of helper functions on top of that, right? Things which basically take the temperature sensors and so on and perform some kind of utility computations on it and give you processed data, maybe actually convert it into centigrade or Fahrenheit or whatever units you want, or derive extra things like, is the temperature too hot, too cold, is there some other thing that needs to be performed, some other kind of event that needs to be generated based on the current temperature, and so on. And finally, on top of all that, you have your actual software, the application that you are developing, which basically says, okay, if the temperature is too hot, do this, or if the temperature is too cold, do this, or if the temperature is just right, then activate a whole bunch of other things, right? Now, as you can see, what is happening is that you have basically abstracted out different layers, and you can actually have different developers working at the different layers of your abstraction. In other words, a hardware engineer could mostly design their system without really worrying too much about what kind of software is finally going to run on it. But you need to keep in mind that in general these divisions are not hard and fast, right? A hardware engineer who designs the system without any knowledge of how drivers work is probably going to create problems for the driver software and also not really do the best possible design from the hardware point of view, right? You might put in features that can never be used by software, for example. A person who writes drivers but doesn't understand software is going to have difficulty writing those drivers. At the same time, if you don't know what is going to be done with the data generated by your drivers, that also is not good news. So at the very least, you can see that there is like cross-layer flow of information, leakage of information, so to say, right? The goal is to have the distinction between the farther layers to be as clear as possible, but at the end of the day, a person who knows how software works as well as how the hardware it's running on works is going to be able to build a better system because they have a more unified sort of view of the entire system being designed. Of course, this is not restricted to the area of embedded systems, right? But we are looking at it primarily in that context. And as you can imagine, at any given point, there are many different variants of how the layering itself can be implemented. As an example, we have already looked at some of these things. We have first the hardware abstraction layer, right? Or this is basically the drivers, so to say, right? Or at least very close to the drivers, but this is the closest that you can get to the hardware while still being in the area of embedded software. So what are the kinds of functions that we have over there? There would be something which basically says, write to a pin, and you would have some kind of low level codes that basically set low level code that basically sets the value in a particular address, which in turn goes into a register and causes something to get updated. You could also have something which basically says read pin, right, which reads from a particular location and tells you what the value of a pin was. Maybe it's a button that's been pressed or not. Okay, so this is at the lowest level, literally right next to the hardware. Drivers could be one higher level of abstraction where I could basically say, okay, now I need to know it's not just a pin, this is actually maybe an LED, some kind of a light that I'm interested in controlling. So I need to have something which basically allows me to initialize that particular driver. It stores some kind of state which basically tells me which pin corresponds to which light fitting that I have. And rather than going and directly saying write this into this particular register, which is what HAL GPIO write does, I now have a function which basically says turn on the light, right? In turn, all that it does is it calls HAL GPIO write pin, but I have now abstracted it out and I can now think in terms of turning on or off a light. So this is the driver level. Go one further level and I can actually think in terms of lighting control. I have a controller which is there on top of everything, right? In this case, it might look trivial, right? I mean, what exactly are you doing over here? I basically have a light driver on, light driver off, or you could potentially just have something which says light driver on of 1 or light driver on of 0 in order to turn on or off a particular setting. But the point in this middleware is that you are now thinking in terms of the controller that you are actually building around it, right? What kind of responses should be possible? The direct control is you can turn on or off the bulb. What this is providing is a little bit more complicated functionality which says based on perhaps some kind of logic that you have, under what conditions should it turn on, what kind of checks should be performed before you turn on or off. You could add all of that logic in here, right? And finally, you have an application which basically says, show a GUI, check for any buttons that have been pressed, maybe accept commands that are coming in remotely through Wi-Fi or Bluetooth, and then decide to turn on or off the control. The application layer typically talks directly to the controller layer. The controller layer talks to the drivers talk to the hardware, right? So at the application layer, I don't really know or care about which GPIO pin is connected to which bulb, which means that I could also retarget my entire application from an ST micro processor to a Raspberry Pi or to a Atmega, right, without having to make changes throughout my entire code. So this kind of layered architecture basically helps us to create different layers of application logic and structure the code that we have. So the benefits, obviously, you have modularity, you have reusability, the core functions, the drivers and even the middleware can be reused in different applications. It's scalable. If I had a new kind of light bulb or a new kind of actuator that I wanted to add into the system, I could just concentrate on extra functions for that without having to modify the rest of my code. And the entire system is also more easily testable because I can sort of write unit tests that test each of these individual functionalities without necessarily being concerned about how the overall system works. Now, the layered architecture is one sort of common pattern. Another very common pattern, especially in the context of embedded systems, an architectural pattern, is something called the event-driven architecture. Now, in order to understand what we mean by an event-driven architecture, we need to think in terms of loosely coupled systems. What I mean by loosely coupled systems is you have different sort of sensors, actuators and so on, right, which it could be that, I mean, yes, you have a single controlling program that basically needs to read the inputs and respond and so on, But you might also have a scenario where, for example, maybe some of the sensors are not expected to be active all the time, or some of the actuators are not expected to be connected most of the time, right? In fact, even in something like home automation, you might find that maybe the TV or the microwave is not really even powered on. So then what should happen? A normal, a layered architecture might still say, hey, go and look at each and every one of these things and see what their current state is. Whereas I might, on the other hand, say, somebody brought in a new system. Okay, now how do I couple that into my entire application without disrupting everything else that already exists? So you have a scenario where there are many entities, each of them working independently or semi-independently. They don't have a very sort of close interaction with each other. They do of course generate events that other entities need to respond to, right? So even in the context of home automation, maybe pressing a button, temperature, crossing a threshold, each of these are events, and you would like to have a system where, yes, based on the events there is some kind of a response, but at the same time if some particular part of the system doesn't respond or is not there, the system just continues without really sort of breaking down because of that. The common way by which this is done is by using again the idea of callbacks, right? And also of having some kind of ISRs, interrupt service routines, are a very common way of handling things like this. Events and interrupts are very closely related, right? At the hardware level you have interrupts, in the software level you basically can think of them as events. An interrupt being generated on a system is some kind of an event, which means that you could then translate it and say, okay, pressing a button can be treated as an interrupt, which in turn triggers an event, right? But you might also have events generated in other ways. For example, by comparing a temperature reading against a threshold, you might generate an event. Now that's not necessarily an interrupt, but it was still an event that needs to be responded to. The underlying sort of way of treating both of those is similar in both of these cases, right? Now if you are using an ISR, an interrupt service routine, then you basically have that as an ideal way of delivering an event notification. The ISR responds typically by calling some kind of a callback. So once again you have the callback pattern that we had already discussed, right? You register a set of function pointers, right? And by having the function pointer registered as a callback for a particular event or an interrupt, it means that when that interrupt occurs, that function pointer, or in turn that function, basically gets called. So the event manager code itself is fairly simple. Basically what it says is you can put all your events into some kind of a queue, right? And a queue is basically what's called a first in first out kind of data structure, which means that if I have multiple events, a whole bunch, several different buttons being pressed, some kind of temperature alarms going off, I need to process all of them. I can't do all of them at the same time. What the ISRs or the callbacks are going to do is just keep putting them into queues, right? And after that I can then basically go through that queue, pick out the events one by one, and then for each event I basically look at what are all the handlers that have been registered for that event and call them one by one, right? So a single event can basically trigger many different handlers. The idea of the observer pattern comes into play over here, right? But this is an explicit way by which this basically gets implemented in terms of events. What does an event handler itself look like? That could be very simple, right? It just basically says it looks at what kind of event happened and based on that decide what functionality needs to be performed. Okay, turn on or off a light bulb, right? So things like this could basically be written in a very sort of clean manner where you can basically think in terms of events and the corresponding changes that need to be performed as a result of those events. So event driven architectures, the biggest advantage is responsivity, right? They can be made highly responsive to external inputs, right? Simply because of this close connection with interrupts and so on, especially in systems where there are unpredictable inputs, or as I said, where you want loose coupling between components, where there is a chance that some components either fail or are not there for whatever reason, right? Now On the other hand, they can also be very complex to debug because interrupts ultimately are breaking the execution flow of a program. Anytime an interrupt happens, it's an asynchronous event. It is not the standard sort of control flow that you were expecting. It is taking it somewhere else and forcing it to behave in a different way. And there is also this term callback hell, which basically sort of says that you can end up in a scenario where a particular event calls back a function that in turn triggers something else that triggers some other events, and you can basically end up in a scenario where you don't know how you ended up in a particular function, or at least it becomes very hard to keep track of it. Okay. Now, two patterns we have looked at so far: the layered architecture, the event driven architecture, which ultimately in some sense takes you to the notion of an operating system, right? And over here, especially in the context of embedded systems, that the first step towards that is what's called a microkernel. A microkernel architecture comes into play when your application has grown to a point where you need more complex interactions. Maybe you need to write data into files, you need to communicate over a network. You have multiple peripherals and drivers, all of which you need to keep track of, right? It's not just a temperature sensor and an air conditioner. There are logging systems, there are visualization systems, there is monitoring, a whole bunch of other things that require additional code software, right? At which point you probably want to start thinking in terms of having all of these different drivers and so on interacting in a certain way. Now, the kernel, right, this word kernel is used to refer to the core part or the core functionality that is going to get triggered whenever a system is operational, right? And the idea of a monolithic kernel is that it's a single block of stone, so to say, right? I mean, it's all carved out of a single block of stone. That's what the monolith stands for. Where you have one program, so to say, whose job is controlling everything that's happening on your system. Okay. On the other hand, especially in the context of embedded systems, there is a tendency to move more towards what are called microkernels. And the idea of a microkernel is, rather than having one operating system program that does all the resource management for you, you break it up into small portions, right? Each individual drivers and so on, each of which has a very specific task, and they perform some minimal resource management, including things like inter-process communication, where they can communicate between the different processes, and you have some form of task scheduling. Now, all of these are concepts that we'll look at in more detail when we actually get into the notion of operating systems. But already you can see why perhaps something like a plain layered architecture which evolved into an event driven architecture may not be sufficient, and you actually need to get into something which allows you to actually create a more complicated operating system. That's the idea behind a microkernel. So there are a number of other different architecture patterns which I'm not getting into. You might come across terms like message passing based architectures, component based architectures, client server architectures. A lot of these are not necessarily in the domain of pure embedded systems, but the point is that the definition of embedded system itself is kind of fluid, right? You could very well end up with an embedded system where there is actually multiple different networked components communicating with each other, and the entire system needs to be thought of and designed in a way that it performs some useful function. Now, an important thing that I want to sort of emphasize again over here is, many of these architecture patterns are not mutually exclusive. It is entirely possible that they overlap. In particular, things like the hardware abstraction layer are going to be found everywhere. Whether it's an operating system, whether it's an event-driven architecture, a layered architecture, a message passing architecture, at some point you have a hardware abstraction layer. Terms like drivers, interrupts and so on are common. They are going to be found in pretty much all of these systems, right? So rather than just trying to pigeonhole and say that okay, this is a layered architecture whereas this is some other kind of architecture, the important point is to be able to understand what are the relevant properties, so that you can then say, okay, can I take some ideas from this kind of an architectural pattern and apply it in this context in order to get a better system or to build a better system. So with that in mind, let's take a quick look at two examples, right, to sort of see, okay, how would you go about, or what might guide the choice of, different architectural patterns in certain cases. So let's say you have a company that's developing a smart home security system. Okay, now I generally don't like this word smart because it's not really, it's got to the point where it's not really conveying any useful information at this point, but it's a common enough term. So we get the idea. When we use the word smart, it means that it is sensing, actuating based on some kind of computation that's performed. The point is there are multiple sensors throughout the house. You want some kind of a central control panel with a touch screen. You want a mobile app for monitoring. You want different kinds of smart devices, real-time alerts, video recording, software updates. You look at all of these things and you start thinking, okay, how would I go about defining architecture, a system architecture? The point is these are the requirements against which you are designing, right? And coming up with a complete set of requirements by itself is a very major part of how you go about designing. Now the question becomes, what kind of architecture should you pick for this, right? And if you think about it, okay, yes, you probably could benefit from having a complete operating system and so on. But on the other hand, if you look at it, the sensors and the actuators over here are not very complex, right? So the questions, the observations that we can make are, number one, you have unpredictable inputs, right? Both user interaction as well as sensor activations are asynchronous. You cannot guarantee at what time what kind of input is going to come. In many cases, you need real-time responses. You need to be able to respond to something that happened, right? And you could have multiple asynchronous events. And one of the requirements over here from all of this, right, the real-time alerting and so on, should basically be about high responsivity. Okay? So all of this, of course, I have sort of picked and chosen to guide this thing, but you can sort of see that there is some kind of loose coupling over here. What I mean by loose coupling is you can sort of see that maybe if one of the sensors is pulled out or replaced or a new sensor is added somewhere else, it should be possible to just have that also sending new messages into the system and having the entire system adapt to that. Event driven definitely sounds like a good candidate in this scenario, right? Now please note that I am specifically saying it may be the most suitable, right? You may come up with other kinds of architectures. You may have message passing architectures and say that, hey, everybody passes messages to a central controller, but that's not really what's happening. You actually want event driven. You want fast responses to events. You want some kind of a structure that sort of allows you to build a system that's going to respond quickly in real time to the occurrence of events. And therefore, that is why we basically feel that maybe the event driven pattern is the right kind of architecture for this problem. Okay, let's look at another example. You are responsible for designing a new pump for some kind of hospital use, medical use, right? Now medical use automatically means that a new set of requirements comes into play. You need precise control over what is happening. It's not just a question of, okay, if a little extra fluid goes in, it doesn't matter. Your pumps have to be accurate and they have to be monitored carefully, right? There could be things where you have continuous modes of operation, intermittent, patient controlled, different ways by which the particular actuators need to be triggered. And more than anything else, you will find that there are a lot of things out here which revolve around this idea of safety, reliability, and alarm systems, right? For any kinds of fault conditions, you should have like very quick detection of fault conditions and so on. You probably need some kind of good user interfaces because the people who are going to use this are not traditional engineers. They are people who are using it for a very specific purpose. So you cannot expect them to be technologically savvy to the point where they, of course, a doctor or a nurse is going to learn the tools of their trade and use it efficiently, but you should not sort of make it unduly difficult for them to use the tools that they need. Also, you probably have a lot of network related activity because you have to log the data, you have to integrate with hospital information systems and so on. Where is this headed? Maybe a microkernel provides a lot of the different kinds of user interaction, networking and so on. But apart from that, it also provides isolation between the different systems that you have, right? So you need to have strong safety and reliability guarantees. You want it to be modular so that each of these things don't really interfere with the others. The core functions which have to be guaranteed to work correctly versus additional services which even if they don't work, it's not a life or death scenario. Those kind of separations, all of those are places where a microkernel based architecture, an operating system, can really shine. Like I said, you could come up with arguments why a different architecture could make more sense over here, right? But at the end of the day, whichever one you choose, you need to be able to pick the right set of properties from it and build on top of that.